Welcome back. Now, locals.tf. Remember what a local is: the manager's internal memo, the board on the wall that only the code can read, not user input, not output, computed facts, defined once, reused everywhere. This file does three things. 1. It calculates the address layout for every street inside every neighborhood. 2. 2. It applies the same label stamp to every road, every junction, every sign we build. 3. It names every permit list in the transit gateway junction. Let us start with the most important one: the subnet meth, CIDR subnet. This is one of the most important functions in all of networking Terraform. And I want to be honest with you. Subnetting is genuinely hard. Hard for network engineers, hard for cloud engineers, hard for people who have been doing this for years. But here is the truth. If you want to be a good cloud architect, you have to be good at networking and subnetting. That is uncomfortable because networking feels like the old world. But the business logic, the application layer, the database, all of it still depends on the network, even in cloud. Networking is not going anywhere, ever. The only difference is instead of configuring switches and routers, doing SVIs and VLANs, layer 2 and 3 security and quality of service via CLI, manually, even via SSH. We write those same concepts in Terraform, and Terraform converts them to API calls. The concept is exactly the same. We still need network. We still need segmentation. The tool changed, the thinking did not. And I want you to remember something important. Remote work is not the same as automated work. Just because you do not have to be physically in the data center does not mean the work is automated. What we are doing here, this is real cloud automation. Before I show you the function, let me say something about subnetting itself. There are so many ways to explain subnetting, many books, many instructors, many courses, each one with their own method, their own cheat codes, their own shortcuts. And there is no single best way. There is only the way that works for you. I have many ways of explaining subnetting: quick ways, visual ways, mathematical ways. But here is the only advice that matters. You find one way that clicks for you, one explanation, one method, one mental model, and you stick with it. Do not jump between explanations. Do not collect 10 different methods and confuse yourself. One way. Master it, move on. So I am going to explain subnetting the best way I can, in a way that connects to everything we have already built together: the neighborhoods, the postal codes, the streets. If this way clicks for you, use it. If you already have a way that works, keep yours. Either way, let us go. Now look at the actual code. 3 values per tier: start, end, new bits. Let me explain each one. New bits, this is 8 for every tier, slash 16 plus 8 new bits equals slash 24. Every street in every neighborhood is a slash 24, 256 houses per street. Start and end. These are the street numbers for that tier. Not one street number, a range. Public tier, start 1 and 3. For production neighborhood 10.1. That gives us 10.1.1.0 slash 24, 10.1.2.0 slash 24. 10.1.3.0 slash 24. 3 public streets, 1 per availability zone. App tier, start 11 and 13. 10.1.11.0 slash 24. 10.1.12.0 slash 24. 10.1.13.0 slash 24. 3 private application streets. Now, why does the code use start and end instead of listing each street individually? Because Terraform can loop. Instead of writing 12 separate cidrsubnet calls, one for each of the 12 streets in each neighborhood, we define the range once: start 11, end 13. Terraform loops from 11 to 13, calls cidrsubnet with each number, and generates all 3 application streets automatically. 6 neighborhoods, 4 tiers, 3 streets per tier. Terraform generates all 72 streets from these 4 range definitions. That is the DRY principle in networking. Define the pattern once. Let the loop do the repetition. And look at how the ranges were chosen. The tens digit tells you the tier. 1 to 3, public, 11 to 13 app, 21 to 23 data, 31 to 33 endpoints. The ones digit tells you the availability zone. 1 zone A, 2 zone B, 3 zone C. So 10.1.22.5, that is production neighborhood, data tier zone B, house number 5. The address itself tells the entire story. No documentation needed, no guessing. Just read the address. 4 types of streets, each one a different zone of the neighborhood. Streets 1, 2, 3, public. The streets that face the main road, visible to the outside world. Your load balancer lives here, your API gateway entry point, the front door of the bank. Streets 11, 12, 13, application. The private streets behind the public ones. Your application servers, your EKS pods. Nobody from outside can reach these directly. They exist entirely behind the public streets. Streets 21, 22, 23. Data. The most protected streets in the entire neighborhood. Your databases, your RDS clusters. No direct access from anyone, ever. Streets 31, 32, 33 endpoints. Service connection roads, where AWS services connect to your neighborhood without touching the public internet. S3, KMS, secrets manager. They come in through here, privately. 4 zones, 4 purposes, perfectly separated inside every neighborhood. One more thing before we move on. Each tier has exactly 3 streets. Not 1, not 5, 3. Why 3? Why 3? Because we have 3 availability zones. AF South 1A, AF South 1B, AF South 1C. 1 street per zone, per tier. Think about it. If your data tier only had 1 street and that zone went down, every database in the production neighborhood goes offline. But with 3 streets, 1 in each zone, your database cluster survives any single zone failure. The application still runs, Seaport still sends his money, the bank stays online. 3 zones, 3 streets per tier, resilience by design. Now, the maths. 4 tiers, 3 streets per tier. 4 times 3 equals 12 streets per neighborhood. 6 neighborhoods, 12 streets each. 12 times 6, 72 subnets. That is exactly where the 72 comes from. Not a random number, not a guess, a deliberate architecture decision written into 4 lines of locals.tf.